All right, let's dive into something that is, and I'm not exaggerating, a truly mind-bending idea. We're talking about a proposal for a brand new theory of gravity. It's called the delta omega hypothesis, and it's a really bold attempt to completely rethink the fabric of the cosmos. So, to get started, let's just ask a simple but really profound question. We're always told that 95% of the universe is made of mysterious stuff, dark matter and dark energy, but what if it wasn't missing at all? Seriously? What if all the strange effects that we blame on these missing pieces are actually caused by a fundamental property of space-time itself that we've just completely overlooked? That's the wild claim we're going to explore today. Okay, so to understand why anyone would propose an idea this radical, we first have to look at the cracks in our current understanding of things, because even Einstein's general relativity, or absolute best theory of gravity, it starts to run into some serious trouble in a few key areas. And here are the big three. First, you've got the idea that at the very center of a black hole, there's a point of infinite density, a singularity, which, kind of breaks the known laws of physics. Second, galaxies are spinning so ridiculously fast they should just fly apart, so we had to invent dark matter as a sort of cosmic glue to hold them together. And third, the expansion of the universe is actually speeding up, so we had to invent dark energy to explain the push. Three enormous problems, and each one needs its own exotic, custom-built solution. So the delta omega theory comes along and proposes this single, incredibly elegant solution to all three of these headaches. It introduces one massive new idea. What if space-time itself has a form of memory? This memory is supposedly carried by something called the coherence field. And the concept here is that the vacuum of space isn't just some empty, passive stage for the universe to play out on. No, it's an active participant that literally remembers the events that happen within it. And that memory can influence what happens next. And this is the crucial shift in thinking, right? In a standard model, space-time is forgetful. What happened a billion years ago doesn't directly influence the curvature of space right here, right now. But in this delta omega model, space-time is more like the wake behind a boat. The past leaves a trace, a cumulative history that physically alters the present. And this is what's so brilliant about the idea. It's just so elegant. Instead of adding two completely different, mysterious things to our cosmic inventory, new dark matter particles, some weird dark energy, this theory adds just one new property to something that's already there, space-time itself. It really aims to unify these problems, not just patch them up individually. So the big question is, how does this one field, this one concept of space-time memory, actually solve our three biggest problems? Well, let's walk through them one by one. First up, the problem of the singularity. This is the idea that matter can collapse into an infinitely dense point where all of our physics just breaks down. A lot of physicists see this as a huge red flag that our theory is incomplete. The delta omega theory just says this never happens. Period. As matter collapses, the coherence field's memory creates a kind of pressure that literally pushes back, preventing a singularity from ever forming. So instead of a black hole, you get what's called a coherence star, an unbelievably dense, stable object, but one without a physics-breaking core. Okay, next up, the problem of dark matter. Stars on the outer edges of galaxies are just moving way, way too fast. According to general relativity, there isn't nearly enough visible matter to hold them in their orbits. They should have been flung out into deep space billions of years ago. So here, the theory suggests that the collective memory of all the matter that has ever existed in and around a galaxy creates what it calls a coherence halo. This halo of influence stretches way beyond the visible stars, creating the extra gravitational pull that's needed to hold the galaxy together, all without a single new particle of dark matter. And finally, we've got dark energy. Our observations show the universe's expansion isn't just happening, it's accelerating. The standard explanation is some kind of constant energy that's just built into the vacuum of space, often described by this number, -1. But why this energy exists, or why it has this specific value, is a total mystery. The memory hypothesis offers a much more dynamic and, honestly, a kind of poetic explanation. The cumulative memory of the universe's entire 13.8 billion year history just builds up over time. This vast cosmic memory generates a pressure that pushes space-time apart, and that's what causes the acceleration we see. It's not some weird constant. It's a direct consequence of history itself. Now, this all sounds fascinating. It's a great story. But a theory is only as good as its predictions. To be taken seriously, it has to offer a unique, testable sign, a smoking gun that we can actually go out and look for. And this theory has one. So how in the world could you test for something as abstract as space-time memory? Well, if these coherent stars really do exist instead of black holes, they should behave differently. And the answer for how to spot that difference lies in gravitational waves. See, unlike a true black hole, which has an event horizon that just sucks in everything, a coherent star would have a physical surface, a memory boundary. This means when a gravitational wave from some cosmic collision smacks into one, most of the wave will pass through, but a tiny part of it should actually reflect off this boundary, and that would produce a series of faint, delayed echoes right after the main signal. And what's really exciting here is that this isn't just some vague idea. The theory makes hard, numerical predictions. For a coherent star with specific properties, a certain mass, a certain size, a certain memory timescale, it predicts that these echoes will be perfectly, evenly spaced in frequency. This creates a signal called a frequency calm, a clean, unambiguous pattern that general relativity says should absolutely not exist. If our gravitational wave observatories ever find that signal, it would be revolutionary. So let's just bring it all home. The delta omega hypothesis presents this really compelling unified vision. It argues that the so-called dark sector, dark matter and dark energy, isn't made of exotic undiscovered particles or mysterious energies at all. Instead, it's an emergent property of space-time itself. The whole thing is made of the universe's own memory, a cumulative history written directly into the very fabric of reality. And that leaves us with a final, fascinating question. If space-time truly does have a memory, what other secrets, what other histories might be stored in the vacuum all around us, just waiting for us to figure out how to read them?